Hi, this is Tom, and this is our recording of the third class in our series on science and Christianity. Um, Last time, we had talked about how the Greeks observed and reasoned about nature, both the heavens and the earth. They had philosophy, formal logic, geometry, and number theory, but did not invent proper science. Now, nevertheless, the Greeks were quite respected, um, for hundreds and hundreds and hundreds of years after um, the Roman Empire fell. Even into the Dark Ages, Aristotle was pretty much considered the smartest guy in the room. Okay, so that's what we covered last time. Um, this time, we start out still in the dark or Middle Ages. Um, and we find that the stage is set for new growth. The church founded modern general purpose universities starting around the 12th century. So, up until this time, the church had theological academies, but the universities were different. They were general purpose schools that studied creation, that studied the world around them, that studied the heavens. And um, this would prove to be a critical development. Um, Both the Catholic Church and the Protestant churches, once the Protestant Reformation occurred, um, founded universities. And one of the motives that seemed to drive them was um, theology developed by Augustine and some other theologians in his orbit, in his same vein of thinking. There was the notion of faith-seeking understanding that since God had created everything, the book of nature it offered us a lot to learn, and so we should study generally the world around us and the universe, and then that would help us know more about God. And with this idea of faith-seeking understanding, um, there was room for questioning. There was room for um, academic freedom. There was tolerance for thinking thoughts and exploring ideas that perhaps would have quickly offended someone's strict idea of doctrine before. So this was a key thing as well. In passing, I'll note that we're going to see here that the entire modern enterprise of science comes out of these church-founded universities. So, you know, too often you hear people say that Christianity is in opposition to science or it's not good for society. They don't usually factor in the fact that the entire modern university system on which science in which science developed, that was critical to science, as well as all kinds of other social institutions like hospitals and the like, were actually founded by churches. But I'm getting ahead of myself. So with these general purpose universities, um, just like the Greeks before them, the Christian world will now engage with both the heavens and the earth, but from a very different mindset, one willing to question everything, including the most respected human understanding to date. So first, let's look at how the Christian world engaged with the heavens. Nicholas Copernicus um, found contradictions with Aristotle and Ptolemy. Okay, let's remind ourselves of what Aristotle and Ptolemy's model the universe looked like. The Earth rested at the center. Um, all heavenly bodies moved around it in perfect circles, with a few exceptions. Okay, um, the heavens were perfect for the most part. Things move through the heavens in perfect circles. However, these wandering stars or planets that the Greeks had identified complicated the model, since they shifted their position relative to all the other stars that just seemed to circle around um, the North Star at night from the northern hemisphere anyway. They had to develop a complicated system of movements for these planets that were called epicycles, and they look like all the loopy things we see on the left in Ptolemy's model of the solar system. Okay, so in order to fit in the few exception cases of these wandering planets that didn't move like the other stars, they took a simple model, basically everything going around the Earth, which seemed to be the case, and they force fit the movement of the planets into that model, and this is what they arrived at. Okay, now Copernicus took a different view. He did something that's more characteristic of today's science. He took these special cases and, without trying to fit them into a predetermined model, asked what it is that these special cases really told us. Okay, and after careful thinking and some double checks where he had specific observations performed to verify his developing thinking, in 1543, Copernicus proposed that Earth and all the other planets, in fact, revolve about the sun. And counter to our experience, the Earth is not still, but it itself rotates about a tilted axis. And that explains the movement of the stars we see, the movement of the planets, and the seasons. Okay, we still have the moon revolving about the Earth, just as Aristotle thought, but everything else goes about the sun. So Copernicus thought it was a marvel of God. He was a Christian. Unfortunately, he didn't get solid reviews from church leaders. But let's just look at the overall proposal that Copernicus made. The picture that Aristotle and Ptolemy had of the universe on the left, very complicated, became the much simpler version on the right. Okay, so it fully accounted for all the motions that we see in the night sky, all the apparent movement of the stars and planets that we see in the night sky, as well as the movement of the sun and the moon. We can see how that happens. The apparent movement of the planets relative to the background stars can be explained just by kind of looking at what we would see from Earth from Copernicus's new model. So just as an example, the little blue dot going around the sun, the yellow dot in the center faster than the red dot, which is Mars, every now and then, well, it's constantly changing positions with respect to Mars. Okay, so now one thing to keep in mind is that when we look at the nighttime sky, all the stars seem to be projected at the top of the sky, so whatever direction we look in, we visualize the star kind of at the top of our atmosphere. Same with the planets. So as the position of the Earth changes relative to Mars, sometimes Mars seems to run ahead of the other stars, sometimes Mars appears to fall behind. And if you remember our earlier class, there's even a little loop that happens, which this video is not showing, that explains, well, that this video doesn't explain, but we can even work out how that little, as Mars goes ahead or behind the other planets, or the fixed stars in the background, it also seems to wobble up and down due to the relative position of the Earth and the Earth's tilt relative to Mars. So all this explains pretty well the apparent, retrograde motion of the planets, and we could look at Jupiter and the other planets and see this. Well, this was all a big improvement over Aristotle and Ptolemy. This picture of the universe, as far as they were concerned, this picture of the universe fully explained the seasons. Now, you may remember that from an earlier class that Aristotle basically had a whole rationalization as to why the seasons occurred. That the sun would kind of drift north, cause additional rainfall, which would produce additional wind that would blow the sun back across the equator to the south, where the sun would cause additional weather like rain, and then winds would result and kind of blow the sun back across the equator to the north. And so the summer and the winter would occur in the different hemispheres. Copernicus makes a lot more sense. When the Earth, which has a constant tilt relative to the sun, the plane that the Earth orbits around the sun in, when you're on, like in northern hemisphere summer, you're actually leaning toward the sun. The rays of the sun hit the northern hemisphere more directly, and some parts of the uttermost north don't even get nighttime, because as you look at the Arctic Circle way up there, it's constantly in sunlight, even as the Earth rotates. But in northern hemisphere winter, the opposite happens. The northern hemisphere, when the Earth is on the opposite side of the sun, halfway through the year, actually tilts away from the sun. The sun's rays hit it less directly. There's less warmth, and in fact, the Arctic Circle is in constant night at the midpoint of the northern hemisphere winter. So big improvement over Aristotle. The seasons are well explained here. Now, as I said before, in Copernicus's model, the moon still continues to orbit the Earth, just like Aristotle thought. So if we look at the overall path of the moon as the Earth orbits the sun, you end up getting this little wiggly dance that the moon appears to do relative to the sun. But it's not an epicycle. It's kind of like just the combined motion. The moon's going around the Earth, the Earth's going around the sun. If you combine the motion, you get this kind of wiggling that the moon is doing around. So still far preferential to the whole epicycle system, because we can see that the moon is actually going around something. It's not just some mysterious thing like the epicycles appear to go around some imaginary point on these crystal globes that rotated about the Earth. So again, everything's quite well explained. Well, so Copernicus's model seemed to be a big improvement, but it wasn't necessarily a hit with church leaders. Now, funny thing is, we should make a distinction between the Catholic and the Protestant church at this point, because by the time of Copernicus, the Reformation had happened. I think we're in the 1500s, and far enough along that the Reformation had happened. And so the Catholic Church, apparently the Pope at the time was favorably disposed to scientific discovery, and initially found no problem with Copernicus's view that the Earth went around the sun. However, Luther and Calvin were a lot less accepting of this idea. Calvin said it was foolishness. Remember that all of us here on the Earth, we don't feel the Earth rotating from day into night. We don't feel the Earth revolving about the sun during the course of the year. We don't feel those things. To us, the Earth seems not to move. Calvin thought it was just foolishness. Luther, in particular, thought it was heretical. Now, he didn't clamp down too hard. He allowed the ideas to be taught. Even where he had influence to stop, where he could have stopped the ideas from being taught. But he did find it heretical. He didn't say a lot about it. It wasn't a big focus for him, but he basically thought it contradicted a verse in Joshua, where Joshua had asked God to, give them more time to win over their enemies, and God had basically caused the sun to stand still in the sky, and the day was extended in length, and Joshua had time to have victory over his enemies. Well, Luther argued that apparently the normal motion of the sun was to move, and the miracle here was that God made the sun stand still. Now he's taking the all this very literally, and he's taking all this as very technical description of the motion of the sun and everything. He's taking this very literally, and he's saying, so what Copernicus is saying in that the normal motion of the sun is to go, the Earth is go around the sun, not the reverse. That actually contradicts, or seems to be in contradiction to, what we read in Joshua here. Okay, now let's just let that sit there for a bit. I want to actually talk about some of the people today who who deny the basic model that Copernicus came up with. There are people today who are called flat earthers. There's even a whole society called the Flat Earth Society, and they don't believe the Earth moves either. Okay, but they usually there are a number of verses in the Bible that are almost the same, and they usually, and same wording, same Hebrew word underneath. An example of the verse, one of the verses they actually point to, which are like largely repeating each other, is Psalms 104:5, where it says, "He set the earth on its foundations; it can never be moved." Well, why didn't Luther strengthen his case against Copernicus with this verse? And the reason seems to be that Luther was a better Bible scholar than today's flat earthers. The thing about this verse, Psalms 104:5, when it says it, when it talks about can never be moved, there are other verses in the Hebrew Bible that talk about how the righteous cannot be moved. Same Hebrew word. And it doesn't mean that we're all mannequins or we're all frozen in place if we've been justified in Christ, or if we're righteous before God. It means that the course of our life can't be shifted away from what God's plan for us is. That God protects us. We're on a road that cannot be shifted. Okay. So it doesn't mean that we have zero motion. It doesn't mean that we're frozen in place. And Luther knew this. He knew that Psalms 104:5 would not imply that the earth couldn't move around the sun. It could just as easily mean that the earth's course around the sun is not shifted away from what it should be. So Luther didn't refer to that verse, but today's smart flat earthers do, because in the English translation it looks like an argument against the earth moving. Okay, just because the coincidence of translation and being very literal on what the words mean. Okay, so Luther viewed it as heretical because of the verse in Joshua. Unfortunately, the Catholic Church came to eventually agree with the Protestants in this regard, and so eventually Copernicus was considered heretical by them too. Now, it's before we go on ahead, I just think that there's a lot that we can learn here. There's a great deal we can learn here, which is just like Jesus talked to the Pharisees and tried to tell them that they couldn't treat the Bible as a legal document. I think what we can learn here is we cannot treat the Bible, the context of the Bible, as if it's a science text. It wasn't written that way. It wasn't meant that way. When we have a strict literal reading as if the Bible is a science text, we are risking putting our own ideas into what the Bible says. Okay, so instead of theology, we're coming up with meology. What am I putting into the text that isn't there? And that's not what we should do. I think from the episode where the Protestants and the Catholics eventually found Copernicus heretical, but yet we know today that Copernicus was right. The Earth does move around the sun. I think it tells us, it gives us the lesson that we need to approach God's word and science with humility. I accept God's word as true, but not necessarily any particular interpretation of it, and certainly not my own interpretation of it as inspired. Okay, so it's better to read God's word in humility, not thinking that we know exactly and fully everything and all that a passage in the Bible means. It's better to realize that that we don't have complete depth of knowledge and complete breadth of knowledge concerning what that verse is saying. Even if we do understand the heart of it, right? It's better to understand that our interpretation may not be infallible than to pretend otherwise. And remember what we talked about from Daniel chapter 12 before, when Daniel said, prophet of God, I heard, but I did not understand. We should keep in mind that other views and other ideas can sharpen our understanding of God's word. The Bible talks about how we're supposed to teach one another. We shouldn't just automatically say heresy anytime our very specific and very literal understanding of a particular verse of scripture is challenged. So, again, I believe in God's word. I just don't believe in my interpretation of it as being inspired. I want to have enough humility to understand that I'm not perfect in my understanding of God's word. And so it leaves me teachable, because I know this: God can illuminate his word as we live, as we walk in the Spirit, and as we live to God. He can illuminate our word, and he can help us understand what we need to understand. Okay, so beyond that lesson for us, I have a few speculations about why the church ended up viewing Copernicus as heretical. Um, one possibility is Copernicus was challenging their worldview. Their worldview was that humanity was the absolute center, the absolute focus of creation. In importance, it was the focus of creation. Humanity was the focus of creation. So the earth, which is where we are, where humanity lives, right? The earth had to be at the physical center of creation. So it's the reason they read Joshua the way they read it. And Copernicus had attacked a really precious truth as far as they were concerned. Okay. Now, another reason why both the Protestant and the Catholic churches may have not responded well to what Copernicus proposed is that many, if not all of them, have been, all of them who had received educations and who had studied theology, as well as others of them who had had educations in the general purpose universities. All of them had studied Aristotle as an authority, and despite Augustine's proposal, that we should be willing to ask questions, faith-seeking understanding type questions. Aristotle was so revered and so foundational to all their educations that it was just kind of indirectly an insult to all these folks who were leaders in the church. It called into question almost the entire foundation of their education, and so they reacted quite badly. In the Bible, in the New Testament, we read about before the Apostle Paul was the Apostle Paul, when he was still Saul, pursuing Christians to Antioch, to try to make them account for what he thought was their heresy. We know that he had been schooled at the feet of a revered rabbi named Gamaliel. Well, it's the same kind of thing. All the educated people of this time, or nearly all the educated people of this time, were completely schooled in Aristotle, and anything that called Aristotle's views into account indirectly called their own prestige into account. So eventually, time moves on. we can, we see that in the Christian world, people continue to study the heavens. The last great astronomer who had no telescope, um, in the history of science, was named Tycho Brahe, and he had actually had constructed these gigantic measuring devices that kind of look like um, large surveying equipment, and he used them to precisely measure the positions of stars and other observable things in the sky, the stars and the planets, especially. So he continued to refine the understanding of the actual apparent positions of the stars and the planets in the sky. He was a um, the predecessor of Johann Kepler, and Kepler actually moved things quite along. Okay, now one of the things about the Copernican model we didn't discuss was um, it was not perfect either, because despite his innovation, Copernicus still thought the planets moved in perfectly circular orbits around the sun, as opposed to the Earth, but still circular orbits. And that wasn't quite right. Kepler, based on the careful observations of Tycho Brahe as well as his own, and by the way, he had a telescope. It had been invented by that time, and he actually improved the telescope. So he was able to use a telescope for some of his measurements, but he was able to show that, in fact, the planets weren't moving in perfect circular orbits about the sun. Copernicus was very nearly entirely correct. They were actually slightly elliptical, which again was quite a challenge to Aristotle, because even that aspect of the perfection of the heavens turns out not to have been the case. The planets moved in slight ellipses around the sun, just slightly squashed circles instead of perfect circles. Okay, so that's what Kepler did. He figured out a number of things. Um, Not only did the planets move in ellipses about the sun, but they moved in such a way that they sped up when they were somewhat closer to the sun, and they slowed down when they were somewhat further away. He was able to numerically quantify this. He made a very careful argument about what was called the laws of planetary motion, but he didn't understand why any of it happened. Okay, so that would have to wait for a. Okay, and that brings us up to Galileo Galilei. He is considered by some to be the father of physics. Um, well-educated guy coming out of the church universities, Christian. He improved his own telescope. Um, he improved the telescope, which allowed him to make lots of crucial observations. By the way, despite being just an all-around physics guy, during most of his lifetime, he would have been thought of foremost as an astronomer. So when he used his telescope, he saw a number of interesting things. He saw the rings of Saturn that were a wonder. He actually was able to use his telescope during the day, and I assume indirectly, because it would be too bright to look at with your eye. Indirectly, he was able to see sunspots crossing the surface of the sun, meaning this source of light and energy for the entire planet was not perfect in the sense that Aristotle had talked about. It wasn't a perfect sphere. It wasn't unblemished. It wasn't just perfectly shiny. It actually seemed to have some kind of structure too. When he looked at the moon, he saw a very cratered surface, not at all a smooth, perfect surface like the type of heavens that Aristotle mentioned. When he looked at Jupiter, he actually discovered that Jupiter had its own little moons orbiting about it. So he was able to see 4 of them with his telescope. We now know there are many more, but he was able to see how Jupiter and its moons were kind of like a little mini solar system. So that made it even easier to believe in the Copernican model of the larger solar system, because you could almost see it in miniature with the moons of Jupiter orbiting Jupiter. Well, Galileo was a very strong proponent of Copernicus because of all this, and that led to trouble. Um, so Galileo was a um, friend to the man who became Pope during his time. They were friends before, amazingly enough. Okay, so um, when the Pope Galileo had known as a friend found the Copernican model heretical, Galileo wrote a little. It was called a kind of a play or a dialogue. It had two characters, and there was one wise, intelligent character, and there was another. He talked back and forth with a really slow-witted character whose name was Simplicio. Um, Everyone who read this at the time apparently thought that, basically it was a caricature. Simplicio was a caricature of the Pope. And the whole purpose of this dialogue was to show Simplicio how foolish it was to deny the views of Copernicus. So it was taken to be a direct insult by Galileo's former friend, the Pope, and he put Galileo under house arrest for the rest of his life, starting in 1633. Um, Now, fortunately for us, Galileo had studied physics more broadly than just astronomy. Throughout his life, he had also talked about motion, okay, or he had been interested in motion, and so I believe he continued his work on motion when he was under house arrest, and he made some really giant contributions. Well, if we go back to his earlier life, even before he was stuck at home, we see that he was a very shrewd observer and a very careful observer, and also had developed an interest in motion. So in these large churches, these cathedrals of Europe that Galileo was used to attending, there were these very large light fixtures that hung down over a very significant space, and usually they were very high up off the floor. They generally had lots of candles or lots of oil lamps that could illuminate the space. And so there were different techniques to light these candles or oil lamps as needed. But one thing they did was they were able to kind of, grab the supporting rope or cable from the side and pull it over to a mezzanine level and light it there, and then kind of try to gently put it back so they didn't blow out the candle or the flame of the oil lamps. And yet, if right after they did this, this large light fixture would be kind of rocking back and forth. And so what Galileo observed, even as a young man, was, and this would not be expected, is at first the rocking motion was pretty wide. It was a big arc, and then it would settle down and get to be a smaller and a smaller and smaller arc. But what Galileo noticed was that even though eventually the rocking would stop, until it did, the time it took to rock back and forth was the same, even as the rocking kind of calmed down and the arc became smaller. So, like, if it took a second for this large light fixture to rock back and forth, as when it was rocking back and forth by maybe 5 or 6 feet, it was still taking a second when it was just rocking back and forth by 1 foot, and it was still taking a second when it was just rocking back and forth by inches, almost not even noticeable. So Galileo realized that, hey, this would make a really good way to keep track of time. Okay, so he actually designed a whole clock based on this idea, and you can kind of see on the left where you have this looks like kind of a mallet rocking back and forth. There's some sort of a ratchet mechanism, so when it rocks in one way, it causes the gears to turn, and when it goes back the other way, it doesn't cause the gears to turn. So it kind of advances the gears by one tooth, so to speak, in a way that causes a clock to keep good time. And a modern example of this sort of clock is the grandfather clock that you may have seen, which we have an actual kind of a photo image on the right of a grandfather clock. And you see that big bob thing that you might have noticed here and there as you've seen grandfather clocks. Well, that's kind of like the mallet in Galileo's design. So that's a modern version. Well, it turned out that this kind of timekeeping, and there was a very, very related type of timekeeping that could occur with a spring, which kind of behaved the same way. You could cause springs to cause something to rock back and forth in the same way as the pendulum. These two mechanisms turned out to be the basis of a much more accurate system of timekeeping than had been available before. And right up until the modern era, when we start having quartz wristwatches and things, up almost all the way until the modern era, this was probably the best timekeeping you could have. Most watches ended up being based on the spring system. Okay, so Galileo's observations about um, a rocking motion back and forth being the basis of good timekeeping were very valuable. But Galileo was interested in motion in a more general way. One of the things Galileo had done was dropped two different lead balls from the Leaning Tower of Pisa, which honestly seems just made for this type of experiment. There was apparently a heavier lead ball and a lighter one, but they were both made out of the same sort of material, the same density, and they had the same shape. And he discovered that they traveled at about the same rate. So, excuse me, it appears that Aristotle was incorrect, that the cannonballs in fact fell at the same rate, even though one was much heavier than the other. That brings us to the need, before going further, of talking about some basic definitions and things that will help us understand as we continue on what's really being talked about. Okay, so let's just spend a few minutes on that. I'll start by trying to make a distinction between distance and position. Okay, so distance is like a length. It's like how far something is away. So if I say that I'm 2 miles from home, that tells the distance, but it doesn't tell exactly where I am, because you also need to know in what direction I am from home, right? In order to know where I am, you can't just say how far. You have to say and in what direction. So position is like distance plus direction, and that does pin it down. So like here in the community, if we leave our front door, we could say something like the dog park is 3/4 of a mile from our front door to the northeast. So that's we could say that, and that's an example of giving a position relative to our front door. Okay, so it's the dog park, called Pubtown, is 3/4 miles from the Friendly Towers. That's the distance, but the position of Pubtown is 3/4 miles to the northeast. Okay, so that's the idea of position. Okay, and it's an example of what's called a vector. A vector is just a measurement of length or something based on length with a particular direction. So those are really useful in physics, and they're going to be even useful in our discussion. Even though we're not going to get very mathematical, this is a helpful concept that we need to understand. Okay, so again, if we consider going from our front door to the dog park, we might appreciate that we couldn't take the path indicated because there are buildings in the way. A bird could fly from the front door to the dog park, maybe, but we would need to go to the corner and then from the corner to the dog park. So, we could think of making the trip that way, and we end up in the same place. Well, the location, or the position, I should say, the position of the dog park is still the same. It's still 3/4 miles to the northeast, from our front door. But the way we got there would actually be by traveling about 38 hundredths of a mile to the east and about 65 hundredths of a mile to the north, one after the other. And you can kind of see that I've traced the path there that we could walk. Of course, there are any number of other paths we could have taken to the dog park. We could start off by walking to the south and just have a big stroll, eventually ending up at the dog park, and it wouldn't matter. The location of the dog park, the position of the dog park is still the same. But because we can take these other little, we can break it up into different, we can break up the trip into, let's say, 2 legs of our journey by going to the corner of the dog park. We can in some ways see that going 38 miles, 0.38 miles to the east, due east, followed by going 0.65 miles due north, that in some ways that's the same as going 3/4 miles to the northeast. And so, again, this is a very helpful concept in physics. We call this vector addition. So like going to the corner, we could call that vector A. It's a certain distance in a certain direction. And then from the corner to the dog park, we could call that vector B, going a certain distance in a certain direction. And the net result of vector A followed by vector B is we end up at the dog park, which we could call vector P, for Puptown, or the dog park. It's 3/4 miles to the northeast. So this is how vectors work. And anything based on length can also be represented as a vector quantity. Okay, so let's consider the idea of speed. I think we're all familiar with the notion of speed in everyday life. For example, if you're in a car on the freeway, maybe you're going 60 miles an hour, right? Maybe 60 miles an hour. You could just as easily say 1 mile each minute. Okay, but speed is the change in length or distance in a given time. So like 60 miles an hour, or 1 mile a minute. Okay, we could even reverse this around, and we can talk about distance could actually be thought of as speed times time. If you go 60 miles an hour for 2 hours, how far did you go? Well, you end up going 120 miles, so it's 60 times 2, right? If you're going 1 mile a minute for 10 minutes, how many miles do you travel? You go 1 mile a minute times 10 minutes, you've gone 10 miles. So speed is defined to be distance per time, and then we could flip that around and we could talk about distance traveled being the same as multiplying the speed by the time. Just another way of saying the same thing. And so thinking about it both ways is kind of useful. Okay, now speed is not a vector. There's no direction to speed, but there is a similar concept that is a vector. And we call that concept velocity. So velocity, whereas speed is a change in distance in a given time period, velocity is the change in position in a given time period. Okay, so for example, if it takes us 50 minutes to get to Puptown, we would say that the average velocity is 3/4 of a mile in 15 minutes, or we could just say that's the same as 3 miles an hour to the northeast. Notice the direction. It's not just 3 miles an hour, it's to the northeast. So velocity is like speed plus direction. So velocity is a vector. It has quantity, 3 miles an hour, and it has a direction to the northeast. Okay, so just like when we were doing position, we can represent velocity as an arrow, and we could even put them together and add them together. Like, you know, if you're a bug walking on the roof of a car, as the car is going 60 miles an hour and you're going 1 mile an hour in the same direction, then you can add them together and you can say you're going 61 miles an hour to the north, say. So so yes, just representing these things as arrows allows us to use geometry, you know, the math that the Greeks invented, to figure out, you know, to figure things out. Okay, so that's velocity. Now there's another concept that is useful, and it's called acceleration. So let's say we got on the big bus here, and we were going to the south at 60 miles an hour, but then we're coming to a traffic light or a stop sign or something of that sort, so we got to slow down and get to a complete halt. Well, acceleration is considered to be the change in velocity in a given time. So velocity is the change in position in a given time, and acceleration is the change in velocity in a given time. So how's our velocity changing? If we're going from 60 miles an hour to 0, well, it's decreasing, right? So the acceleration here is going to be negative. In physics, in everyday life, we would call that a deceleration. In physics, we still call that an acceleration. It's just a negative acceleration, okay? So, but like velocity, acceleration also has a direction. So in this case, you know, we're going 60 miles an hour to the south. That's our velocity, and our acceleration is going to be some negative number to the south, or we could even, you know, consider a negative number to the south being the same as accelerating toward the north. But it's also a vector. Okay. Well, now we're ready to join Galileo in one of his experiments. If we look at the construction Galileo had built on the screen, this amazing piece of physics furniture almost, you know, you can see the craftsmanship with the wood and everything. What we're looking at is what we would call an incline. It's basically like a little ramp, kind of that makes a certain angle with the floor. Okay, the idea is Galileo wanted to stretch out motion so he could study it more closely. When you drop things off a tower, they drop so fast it's hard to really study what's going on. So he wanted to stretch out the fall along this incline so that that he could study how the motion worked. Okay, so what he did was, and let's kind of look at this first, is you know, he had these little brass bells constructed, okay, that he could slide up and down the incline. So he could position these little brass bells along the path, and there was this little you know, like metal striker that hung down from the bell in such a way that when he put a ball at the top and as it rolled down, it would trigger each one of these bells to go ding. You know, it would cause each one to ring, and he could actually slide these little bells around on his inclined plane. So, but no matter where they were, when the heavy little probably lead ball that he ran down, when the ball hit them, it would cause the bell to ding. Now, if we look on the end of this thing, there's a kind of a weight, or like a what we would call a plumb weight today, hanging down, and even though Galileo's pendulum-based clock was never built during his lifetime, he designed it, he drew the graph. During his lifetime, it was not actually used to build a clock, but he still understood how to time things with a pendulum. Okay, so the thing on the end there that's highlighted, the thing on the end there is he would kind of pull it back and let it rock back and forth, and each swing of this thing back and forth, maybe we could call that a tick. So like each tick of his pendulum clock. So it's not actually telling you what time of day it is, but each swing, each tick is taking a certain amount of time. And he used this pendulum to time everything. So this is very ingenious. What he did was he had the little bells slid around on his incline so that eventually when he put the ball in the top and ran it down, that every single time the ball went through one of these little brass devices with a bell and he heard a ding, it would be at the same time that the weight in his pendulum was swinging back to the top of its arc. So he caused the brass bells to be arranged so that the bell rang right on each tick of the pendulum. Okay, and he knew the pendulum was keeping uniform time, that each swing of the pendulum was taking the same amount of time, even though the pendulum might, the rocking might kind of reduce a little bit as the ball ran down the length of the incline. He was able to keep time. So here's the net effect is because each bell rang exactly on one tick of his pendulum, he was able to then measure how far the ball had gotten rolling down the plane each time. Okay, so for example, when he put the ball at the top and he pulled back the pendulum and then he released both at the same time, he could tell that the bell rang. The first bell rang on the first tick, the second bell rang on the second tick, and so on. And then by measuring how far down the incline each of these bells was from each other or from the top, he could see how far the ball had traveled during each tick. Okay, and so this works out to be a way to figure out the average velocity of the ball during each tick. Okay, so during the first tick, the ball went 6 inches down the ramp. That's our direction, down the ramp. The ball went 6 inches, so the average velocity during that tick was 6 inches per tick, right? In the second tick, the ball traveled 18 inches. And so the average velocity it traveled was 18 inches per tick. And likewise, during the third tick, the ball traveled 30 inches down the ramp. So the average velocity was 30 inches per tick down the ramp. During the fourth tick, the ball traveled 42 inches. So the average velocity was 42 inches per tick down the ramp. And likewise, during the fifth tick, the ball traveled 54 inches. So the average velocity would have been 54 inches per tick down the ramp. So it's, what would we say? What do we notice here? Well, one thing we can notice is that the average velocity, the average speed and direction the ball is moving in, isn't the same. Aristotle's theory of motion said that when things dropped, they would drop at the same speed. In other words, to use our new term, Aristotle argued that there would be no acceleration. It was the natural movement of the object toward the earth, and it was whatever was right for that object. It wouldn't speed up, it wouldn't slow down. But when Galileo ran this experiment, he saw that Aristotle didn't appear to be correct. The velocity is clearly picking up as the ball is rolling down this incline. Okay, so we could observe a pattern here. So we see, first of all, that the velocity is increasing. How much is the velocity increasing each time? Well, between the first tick and the second tick, we see, well, during the first tick, the ball went from not moving, which is like zero velocity, to 6 inches per tick down the ramp. During the second tick, we picked, we go from 6 inches to 18, that's 12 inches per tick. And from the second to the third, we get also 12 inches per tick, of an increase in the velocity. And so we see that from each tick to the next tick, we're gaining 12 inches per tick, each tick. So it turns out that that's acceleration. Each gain, each change in velocity during a time period, which is here a tick, you can think of being a second, if that's easier. The acceleration seems to be 12, our change in velocity for each tick is 12 inches per tick, right? So the acceleration seems to be constant. So Aristotle said the velocity would be constant. It wasn't. But what is constant seems to be the acceleration. Another thing we can do is we can look at the total distance the ball has traveled in each tick. Okay, so in the first tick we traveled 6 inches. That's the total. In the second tick we traveled 18 inches, but we'd already gone 6, so now we've traveled a total of 24 inches. In the third tick we go 30 inches, but we'd already traveled 24, so now a total of 54, all the way through to 5 ticks, and when we see that we've traveled a total, if we add up all those numbers, of 150 inches. And Galileo realized there was a pattern here that eventually Isaac Newton will explain, that the total distance traveled by the ball as it goes down the ramp, or the total position of the ball relative to the change in position of the ball relative to the beginning of the ramp, which would be 150 inches down the ramp. So we added direction. But the total is going to be, the total distance is going to be equal to 1/2 times this acceleration we came up with of 12 inches per tick, times the number of ticks, and times the number of ticks again. Okay, now Galileo didn't know why this pattern occurred, he just knew that it did. Well, we also see how Galileo could take this result and even go back to the case of dropping something off a tower, understanding it better too. We see that this incline makes a certain angle with the floor. If we think about tilting this incline more and more and more and more until eventually it's making a 90-degree angle with respect to the floor, then that's the same situation as dropping something off a tower, when the angle is 90 degrees. And so he would have been able to run this experiment for situations like that too. Now, Galileo was also fascinated by the exact path that things would take, given a certain initial motion. So he had another device constructed. Again, beautiful craftsmanship there. I mean, you can just look at the inlaid wood and everything and think, wow, they took a lot of pride in doing this work. But the idea was you put the ball in at the top of the little curved ramp, and then the ball would kind of pick up speed and roll down, and then when it left the ramp, it would be going kind of horizontal at whatever speed. And these little loops, these little hoops, Galileo was able to adjust until the ball would actually travel through each one of them. And what he discovered was the ball did not just travel and then run out of steam and plummet like Aristotle said, but it just followed an arc. you know, to the naked eye, if you weren't carefully measuring things, it might look not very different than what Aristotle said, but it in fact was different than what Aristotle said. So here again, Galileo showed that Aristotle was not right on motion. Okay, so hopefully we have a little taste of how it is that Galileo went about studying motion. Now I would like to talk about something else Galileo talked about, but it wasn't a physical experiment. It was more what scientists call a thought experiment, but a very carefully reasoned out, um, you know, scenario that could be understood. And you know, the basic idea here, the basic understanding that Galileo came up with is called relative motion. It's a really important idea. Later on, we're going to see that Newton and Einstein build on this idea, and so it's pretty important. Let's see if we can understand Galileo's ideas about relative motion. But to start, let's try to understand relative position. Okay, remember what position is? It's a distance and a direction, and it's always it's always talked about in regard to a particular starting point. So here's a family, just happens to be my family. My wife, let's say my wife Missy is our starting point, and let's say that I am 4 blocks in Chicago north of Missy, and let's say my daughter Rosetta is 3 blocks to the east of Missy. Okay, so that means my position relative to Missy is 4 blocks more north, and Rosetta's position is 3 blocks east relative to Missy. Okay, well, where's Missy relative to Rosetta? If Rosetta is 3 blocks to the east of Missy, then Missy is 3 blocks to the west of Rosetta. How about Tom? If Tom is 4 blocks north of Missy, then that means that Missy is 4 blocks south of Tom. Okay, but what about Tom's position relative to Rosetta now? Okay, well, we can kind of draw the arrow, yeah, and it's not wrong. That would show Tom's position relative to Rosetta, but we don't know what that is, right? We don't know the exact distance that is. We don't know the exact direction that's in, right? I mean, as far as an exact angle or something. So let's see if we can figure out Tom's exact position relative to Rosetta, knowing the information that we have. The way to do it is, once again, we're using these vector ideas. Since Missy is 3 blocks to the west of Rosetta and Tom is 4 blocks north of Missy, I can just add these different things together, just like Rosetta was walking this path from where she starts to her mom, Missy, and then from Missy to Tom. Okay, it's the same situation as before when we were adding these vectors together, but the idea here is, by adding these vectors together, the 3 blocks to the west plus the 4 blocks to the north, we can get Tom's position relative to Rosetta. And that's kind of the main idea of Galileo's notion about relative motion. So here, relative position, but we could do the same thing with velocities. Let's look at another situation here. Okay, this is a kind of a thought experiment, right? Let's say we have a boat that's traveling 10 miles an hour to the right. We're just going, or to the east. We can say it either way. It's to the right in this picture. So the boat is going 10 miles an hour to the right. That's the boat's velocity. And let's say there's a ping pong game going on in the boat, down in the boat. But the boat has a nice big window so that you can actually see the ping pong game from outside. Okay, so the boat's traveling on perfectly smooth water. There's a perfectly smooth breeze driving along. No bouncing up and down in waves or anything like that. This ping pong game is occurring. Well, Galileo thought, I don't think he thought of ping pong, but this will be our modern day equivalent to what he thought about. Galileo thought that the guys playing ping pong in the bottom of the boat wouldn't notice any difference in how their ping pong match worked because the boat was moving at an even speed, and so they were kind of on the boat. And relative to each other, they weren't moving because they were both standing in the boat, and the ping pong table wouldn't move because it was standing in the boat. And as they knocked the ball back and forth, it would behave just like any other ping pong game. But let's suppose you're Galileo and you're watching from the shore. So you're pointing your telescope at this ping pong match and you're watching them hit the balls back and forth. Okay, so let's suppose that the people playing ping pong, let's say that the ball is going, as they're knocking it back and forth to each other, let's say the ping pong ball is going 5 miles to an hour, either east or west, depending on who hit it, right? So if the guy on the left hits the ping pong ball to the right, the ping pong ball is going 5 miles an hour to the east or to the right, and as the guy on the left, as the guy on the right swats it back to the guy on the left, the ball is going to the left or to the west at 5 miles an hour. Well, if Galileo is watching this from the shore, what appears to be the case to him in terms of how fast the ping pong ball is traveling relative to him now, not to the players? Well, when the guy on the left hits the ball to the right, okay, at 5 miles an hour, relative to the boat, okay, Galileo sees not just the ball's motion of 5 miles an hour, but he also sees that the boat is moving at 10 miles an hour. So the ball is relative to the boat, moving 5 miles an hour, and then the boat's relative to the shore, moving at 10 miles an hour. So to Galileo, on the shore, it would look like the ping pong ball is traveling at 15 miles an hour to the east, right? Now, when the guy on the right in the boat hits the ball back toward the left, going to the west, okay, now to Galileo, it looks like, okay, the boat's going 10 miles an hour to the right or the east, but then the ball relative to the boat is going 5 miles an hour to the west. So in total, it would look to Galileo on the shore like the ball would now be traveling at 5 miles an hour to the east. Because if we take the vector velocity of the boat at 10 miles an hour to the east, and we add to it the vector, of the ball traveling 5 miles an hour to the west, it's the same to Galileo as if the ball is just traveling 5 miles an hour to the east, relative to himself, not relative to the boat. So that's how relative motion works. Okay, now we could make this seem more interesting. Instead of the boat traveling 10 miles an hour to the right or to the east, we could say, hey, what if the boat is actually traveling smoothly 10 miles an hour to the north? Everything stays the same, except the boat is now traveling 10 miles an hour to the north. So what velocity does the ping pong ball appear to have to Galileo now? Well, we do a vector sum. We add the little arrows together. So the boat, in all cases, is going 10 miles an hour to the north, but then the ball, depending on who hit it, is going 5 miles an hour to the right or 5 miles an hour to the left. So that's relative to the boat. Relative to Galileo, the ball's traveling roughly 11 miles an hour at the angle indicated. And we could use math, geometry, or actually trigonometry to figure out what that exact angle is. And we could easily enough figure out the exact speed. So the angle would give us the direction, and the exact speed would give us the numeric part of the velocity. So this is his idea about relative motion, and it's going to turn out to be very important. But it's also another example of how it is that vectors are useful things to think about. One thing we can think about is Aristotle had rejected the idea that, because it had been proposed to him, that maybe the Earth spins. He thought it was contrary to common sense. But if you think about relative motion, the fact that we're all going the same speed on the Earth as it spins means that we really don't notice it. So relative motion can help explain why why Copernicus was right, even though we don't feel the motion of the Earth. But it's going to turn out to be very important in some other contexts as well. Well, moving ahead, we see that other people picked up the study of motion that Galileo had started, and they expanded this thought. Okay, now I want to tell you that aside from the people we're about to talk about, who go down in science history, there were some people who had studied Aristotle some hundreds of years before, and one of them was named William of Ockham. Okay, and they realized that Aristotle's idea about motion didn't really work. Okay, in particular, things don't just move while you're pushing them and then come to a sudden stop when you stop pushing them. So people who were well schooled in Aristotle and held to Aristotle came to realize that he wasn't right about that. And they had tried to come up with an idea to fix Aristotle, kind of like Ptolemy had adjusted Aristotle's astronomy without changing it too much. They tried to fix Aristotle's ideas about motion, and they came up with a concept called impetus, which was kind of like how much mass something had multiplied by its speed. They weren't able to fix Aristotle's theory of motion that way, but eventually we come to, after the time of Galileo, we end up with a physicist, mathematician, and philosopher named Descartes. And Descartes, along with a Dutch, Descartes was French, with a Dutch guy named Huygens, they saw the emphasis that students of Aristotle had put on this new idea of mass times speed. What they did was they considered it to be a vector. So not just a number, but a vector. So, velocity is a vector. So mass is just kind of like a number. So when you multiply a number by a vector, they said, hey, maybe that's a vector too. Okay? And they called the idea momentum. And what they discovered with this is that if you add up the momentum like a vector, you add the little arrows up like a vector, before and after objects interact, that the total doesn't change, right? So in this case, I'll run a video that will help us to see it. Okay, this is called Newton's cradle, although it demonstrates the property. I don't think they necessarily had Newton's cradle available to them. But what we see here is that when you pull a given number of balls back, the same number shoot out on the other end. Okay, and so this is an example of how the momentum is actually conserved. And that word conserved doesn't mean like we conserve energy. It means stays the same. So in all cases, no matter how objects interact, we observe that if you add up the total of all the momentum, it stays the same. Here's another picture. Let's say we have two balls and somehow they're interacting. Okay, so they cause a change in motion relative to each other. There are all kinds of ways they could interact. Maybe they have little magnets in them, and we'll talk about magnets later. Or maybe they just hit each other. It doesn't really matter how they interact. Even if they're not hard balls, but they're more like lumps of Play-Doh and they stick together, it doesn't matter. In all cases, if you add up the momentum, which is the mass times the velocity, and we preserve the direction when we do that, if you add up the little the arrows indicating the momentum of each of these objects, and you add them together, just like we added the other vectors, you find that the total momentum, the vector total, is the same. Okay, and so this is called the conservation of actually linear momentum. There's another type of momentum that is also conserved, but this, I'll just call this for short, the conservation of momentum. It turns out that this is going to completely set the stage for the advancement of physics. It's also based on this concept of vectors. Okay. Well, all this said, last time I promised you that we were going to try to understand what finally changed between the time of Aristotle and the time of Newton, when science advancement really started suddenly to pick up again. Okay, and I said it was mainly a little Bacon. Well, now we've reached the point. We have reached the point where we've come to Francis Bacon, and what he came up with was called the scientific method. But in some ways, it's just what we've already seen. The key ingredient for the new advancement that was about to take place was the idea that you wouldn't just observe things casually, then come up with a philosophical interpretation of how things work like Aristotle did, but then you would subject that understanding to specific tests, or we call them experiments, and you would see did the results hold up, and you would specifically, and this is what Francis Bacon said, you would specifically try to find exception cases, try to find where it didn't hold up, try to break your own theory, and as you perform those sorts of experiments, you would either observe that your theory seemed to still be seemed to fit all the facts, or it didn't, in which case you would adjust your theory, or you would find new things of interest that you were to think about. This idea of testing, intentionally trying to find where your theories don't work, testing multiple times to make sure that your theories work consistently. This is what we call the scientific method, and Francis Bacon is given a lot of credit for it, although truthfully, in some ways, he was just picking up on what was happening in not just with Galileo, but with other scientists of his day. They were all starting to test things, not just to take them as true, but to test them. And I think that grew out of the academic freedom and the ability to question that they had coming out of the general purpose church universities. So it was the scientific method, the idea of testing, really, that started the real progression of science that leads to our modern day understanding of how things work. We can kind of look at a timeline of physics and see what the effect of all this was. Basically, from the time of Aristotle to the time of Newton was about 2 millennia, or maybe more like 1900 years. A lot of progress didn't happen in terms of a basic understanding of nature. But then when people started testing according to experiment, right, when they started questioning theories that had been developed based on observations, but then not subjected to testing, when they started actually testing these things out and finding where they did and didn't work and trying to come up with new explanations and then testing those explanations, then you have the explosion that resulted in what we call physics today, which underlies all our modern science. Okay, so experiments turned out to be the key ingredient, and we give Bacon a fair amount of credit for that. Okay, another way to look at it is the pace of innovation started to skyrocket after this. You know, there have been innovations during the period from Aristotle to Newton, but they really just took off and exploded after Newton. So this was a key turning point. Also, it coincides with about the time um, coffee was introduced on a large scale to people, so maybe that has something to do with it. But I don't think that fits our facts as well as the idea of the scientific method and experiment, and a kind of a special genius of a scientist like Newton really caused things to take off. Okay, and bring us to the present. Um, Newton was so important that he was, in his time, really considered God's gift to science, and I mean literally. And this is how one poet of the time said it: "Nature and nature's law led hid in the night. Newton said, let Newton, or I'm sorry, God said, let Newton be, and all was light." So I messed that up. Let me read it again. Nature and nature's laws led hid in the night. God said, let Newton be, and all was light. So it was considered that he so unlocked the understanding of nature that it was almost like he was a miracle of God. He was recognized almost as a miracle of God during his time. Um, you know, we've gone beyond Newton at this point, but if we just want to look back, even the greatest scientists in our modern era look back to Newton and say, even in areas where they've gone beyond what Newton said, and kind of added to it or even kind of corrected it, um, no one says anything other than Newton is probably the greatest scientist ever. Like Einstein said, no one must think that Newton's great creation can be overthrown in any real sense. He developed the very way of thinking about physics, and on his work, everything since has been built. Newton himself was a Christian. He was passionate about God. We talked before in our first introductory class about one quote from him: "All my discoveries have been made in answer to prayer." He said other things like, we must love our neighbors ourselves, we must be charitable to all men. And this one I like. It says, "He who thinks half-heartedly will not believe in God, but he who really thinks has to believe in God." He also wrote on theology. He didn't mind having his own opinion about things, so he wasn't trying to just say what other people expected him to say. So he had his own thinking. And he seems to have had fundamental humility about it. He said, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." So he knew that there was a lot more to figure out. He also knew that he didn't start from zero, that his thinking was assisted by other people. And he put it this way. He said, "If I have seen further, it is by standing upon the shoulders of giants." Okay, so I imagine he was thinking about Galileo and others, maybe even Aristotle. Since this time, other people have said almost this exact same thing, expressing their humility or acknowledging that they didn't invent whatever they came up with all on their own. So in a way, he even invented the perfect expression of humility in that context. So it's kind of funny. But one last passing lesson I would like to learn from Newton's life is he said this. He said, I have a fundamental belief in the Bible as the Word of God, written by those who were inspired. I study the Bible daily. And when we go through and look at all the things that Newton came up with, and imagine how busy his life must have been, I think it's a bit of a correction to the rest of us. If we're not as consistent in reading and studying the Bible as Newton, how it is that he could have managed to find time to study his Bible every day, given all the other things that he was doing, which we see the evidence of, right? But maybe he wasn't stealing time from his scientific endeavors. Maybe that was the power behind Newton's science, okay? Well, that brings us to the end. We're not going to get into the detail of today's class. We're not going to get into the details of Newton's life, but we're all primed to get into it next time. So his story will continue. We're going to talk about forces and horses. We're going to talk about atoms and heat, and we're going to have lots of new ideas to chew on. Okay, so that's for next time. Thanks for listening to the class. Bye-bye.